The morning of January 4th, 1945, Kobi Airfield, Taiwan. Lieutenant Charles August pushes his Grumman F6F-5 Hellcat into a steep dive, the Pratt and Whitney R-2800 engine screaming at full throttle as he lines up parked Japanese aircraft below. Bureau number 71441, one of 12,000 Hellcats rolling off American assembly lines like clockwork, 2,400 rounds of 50 caliber ammunition, 212 pounds of armor plate. Self-sealing fuel tanks holding 250 gallons. Every system redundant, every component built to absorb punishment and keep flying. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Then, the engine coughs. Oil pressure drops. The massive 18-cylinder radial that's supposed to be indestructible suddenly isn't. August has seconds to decide. Bail out over enemy territory or try for a wheels-up landing. He chooses the latter. The Hellcat skids across rough ground near the airfield, tearing metal, bending propeller blades. But the armoured cockpit does its job. August walks away from the wreck. Japanese soldiers are already running toward him. Within hours, his Hellcat, Bureau number 71441, is surrounded by Japanese engineers. They've shot down American planes before, examined wreckage, analysed bullet holes and burn patterns. But this is different. This is an intact F6F, barely damaged, every system accessible for inspection. And what they're about to discover won't just surprise them. It will force them to confront a truth they've been avoiding since 1943, that they never understood what they were fighting. The interrogation begins not with questions, but with measurement. Japanese Naval Air Technical Arsenal engineers at Yokosuka have developed protocols for examining captured aircraft. They photograph everything. They measure wingspans, fuselage dimensions, control surface areas. They document the obvious. This fighter is enormous. 12,186 pounds fully loaded, more than twice the weight of a Mitsubishi A6M0. The engineers expected this. Intelligence reports have been consistent about American mass. What they don't expect is what happens when they start disassembling the engine. The Pratt and Whitney R-2800 double wasp comes apart in sections. 18 cylinders arranged in 2 rows of 9. The Japanese engineers, trained on Nakajima Sakai and Mitsubishi Kinsei engines, approach this with professional curiosity. They've examined American engines before, Wright Cyclones from captured B-17s. The principles should be familiar. Then they remove the first cylinder head, and another, and they start comparing parts. Each cylinder head is identical, not similar, identical. The pistons, when measured, show tolerances within thousandths of an inch, ring gear teeth that mesh perfectly with any matching component, connecting rods that could be swapped between cylinders without hand-fitting. Lieutenant Toyoda Takago, one of the engineers assigned to foreign aircraft analysis, records his observations. The report, preserved in Japanese archives, captures the moment of realization. The Pratt and Whitney engine contains 2,840 precision-machined parts. Each part appears to be manufactured to specifications, allowing complete interchangeability. Any R-2800 component may be exchanged with the same component from any other R-2800 engine without modification. The implications settle over the examination room like a physical weight. In Japanese engine production, each Nakajima Sakai requires hand-fitting of components. No 2 engines are exactly alike. Tolerances vary. Parts must be matched, adjusted, filed to fit. It's craftsmanship, individual expertise. The way things have always been done. The Americans have industrialized what the Japanese still treat as an art form. But the engine is only the beginning. As the inspection continues over the following weeks, every system reveals the same philosophy. The electrical wiring uses standardized connectors. The hydraulic lines feature quick disconnect fittings. The gun mounts can be removed and replaced in minutes rather than hours. Even the armor plate, which the engineers examine with particular interest, shows standardized mounting points and interchangeable sections. One engineer attempts to calculate production time. If every part requires hand-fitting, if every engine needs individual adjustment, How many man-hours separate a Hellcat from a Zero? The numbers don't make sense. They can't make sense. The Americans are producing Hellcats at a rate of 500 per month from a single factory. 500. Nakajima's entire production for 1944 was 5,100 fighters of all types combined. The Hellcat's bureau number gets painted over. Japanese markings applied. The aircraft receives the designation Yo-801, registered to Yokosuka Kokutai for flight testing. Repairs take longer than expected because damaged parts can't simply be replaced. They must be fabricated, adapted, made to work with what's available. The irony isn't lost on the engineers. They're hand-fitting repairs to an aircraft designed never to need hand-fitting. When test flights finally begin, the reports describe performance that matches American claims. 380 miles per hour at optimal altitude, 37,000-foot service ceiling, combat radius of 300 miles. But it's the damage tolerance that captures attention. During one test flight, the Japanese pilot deliberately stresses the airframe, pulling maneuvers that would tear the wings off a Zero. The Hellcat handles it. The pilot's report notes, aircraft stress beyond normal operational limits. No structural failure observed. American weight allocation permits safety margins unknown in Japanese design philosophy. These test flights don't last long. Mechanical problems, probably from the force landing damage August inflicted, eventually ground the aircraft permanently. It gets pushed to a dispersal area at Yokosuka, where American forces will find it in September 1945, battered and partially cannibalized, but the data gathered from those flights has already been distributed. The technical analysis section compiles a formal intelligence brief on American fighter aircraft based on the captured Hellcat and other examples. The brief makes its way through Japanese Naval Aviation Command structure. Section commanders read it. Training officers incorporate findings into pilot instruction. The document describes the Hellcat's structural philosophy. This aircraft is sturdy and simple, another masterpiece of so-called Grumman ironworks. Hellcat is what Wildcat is resized bigger and improved faster. But there's a phrase buried in the middle of the technical specifications that reveals more than any performance figure. Describing the captured TBM Avenger examined earlier that year, Yokosuka specialists had noted their surprise at the extremely strong construction. That same phrase appears in reference to the Hellcat. Strong, not clever, not efficient, not elegant. Strong. Japanese fighter design has always prioritized performance over protection. Lieutenant Commander Saburo Sakai, Japan's most celebrated surviving ace, understands this trade-off intimately. He lost his right eye to American gunfire in 1942 when a bullet penetrated his unarmored cockpit. He knows the Zero's brilliance lies in sacrifice, sacrificing protection for maneuverability, sacrificing durability for range, sacrificing pilot safety for combat advantage. In 1943, this seemed like intelligent design, superior. Piloting skill combined with superior aircraft performance would overcome raw industrial strength. The math favored Japan. Until it didn't. The industrial philosophy gap becomes clearer as more American aircraft fall into Japanese hands. A Vought F-4U Corsair, captured near Kasumigora Flight School, surprises engineers when they discover fabric covering portions of the wing. Fabric! On a frontline fighter! The Americans, with all their industrial capacity, still use cloth where Japanese engineers would specify metal. It makes no sense until you understand American design priorities: ease of field repair, component replacement, maintenance, simplicity. The Corsair's fabric panels can be patched with basic materials. Japanese all-metal construction requires specialized facilities. Every captured American aircraft tells the same story. The B-24 Liberator's flight manual, recovered in summer 1944, reveals standardized procedures that assume interchangeable parts and modular systems. The P-51 Mustang's engine cowling design prioritizes maintenance access over aerodynamic perfection. Even small details, quick-release fasteners, standardized bolt sizes, color-coded wiring reflect a manufacturing philosophy built around mass production and field serviceability. If you're enjoying this deep dive into the story, Hit the subscribe button and let us know in the comments from where in the world you are watching from today. Japanese engineers compile comparison charts, production rates, pilot training hours, engine reliability statistics, maintenance requirements. Every metric favors American systems by margins that seem impossible. A Hellcat engine runs reliably for hundreds of hours between major overhauls. A Nakajima Sakai requires constant attention, frequent adjustments, careful monitoring. American pilots receive 250 hours of flight training before deployment. Japanese replacement pilots by late 1944 are being sent to combat with 40 hours. The captured Hellcat at Yokosuka becomes a teaching tool. Trainee pilots are shown the armor plate, the self-sealing tanks, the redundant systems. The instructors explain, "This is what you're facing, not just a heavier fighter. An entire industrial system designed to protect pilots, simplify maintenance, and produce aircraft faster than Japan can shoot them down." But understanding the problem and solving it are different challenges entirely. Japanese industry in 1945 cannot simply adopt American production methods. The infrastructure doesn't exist. The precision machinery required for interchangeable parts manufacturing isn't available. The supply chains that deliver standardized components to assembly plants have been disrupted by American submarine warfare. Even if Japanese engineers wanted to rebuild their entire production philosophy, there isn't time, there aren't resources, there isn't capacity. Professor Jiro Horikoshi, who designed the Zero, will later examine the Hellcat extensively after the war. His conclusion will be devastating in its honesty. "We designed an aircraft for 1941. They designed an aircraft system for 1945. While we were perfecting the sword, they were building the industrial age." That assessment captures what the engineers examining Bureau number 71441 discovered in January 1945. The Hellcat isn't just a better fighter, it's evidence of a better way to build fighters. Every bolt, every wire, every panel speaks to a manufacturing philosophy that values systematic efficiency over individual craftsmanship. That prioritizes pilot survival over aircraft performance. That assumes future maintenance needs and plans for them during initial design. The Zero was built by craftsmen who made each aircraft slightly different, adjusting tolerances, fitting parts, creating precision through individual skill. The Hellcat was built by a system that made 12,000 identical aircraft, each one capable of being repaired with parts from any other, maintained by mechanics who didn't need to be craftsmen, only trained. Two philosophies, two approaches to the same problem. And by January 1945, one is producing 500 fighters per month, while the other struggles to keep existing aircraft flyable. The morning Lieutenant August force-landed his Hellcat on Taiwan. He couldn't have known his aircraft would become a classroom. That Japanese engineers would measure every dimension, test every system, document every design decision. That his Bureau number 71441 would teach them something more unsettling than any tactical briefing. They were fighting an enemy who had industrialized warfare itself. The weight paradox becomes unavoidable the moment Japanese engineers start calculating stress loads. The Hellcat's empty weight, 7,670 pounds. The Zero's empty weight, 3,704 pounds. The American fighter weighs more than twice as much as Japan's primary naval fighter. Every principle of Japanese aeronautical engineering says this should be a catastrophic disadvantage. But the performance figures tell a different story. Maximum speed, Hellcat 380 miles per hour, Zero 331 miles per hour. Rate of climb above 10,000 feet, nearly identical. Service ceiling, Hellcat 37,000 feet, Zero 33,000 feet. The heavier aircraft matches or exceeds the lighter one in nearly every category except turning radius. And that single advantage, the Zero's legendary maneuverability, has become increasingly irrelevant in actual combat. The engineers know why. Reports from surviving pilots have been consistent since mid-1943. American pilots refuse to turn with Zeros. They attack from altitude, make a single high-speed pass, and use superior power to climb away before Japanese fighters can respond. The boom and zoom tactic exploits exactly what the Hellcat's weight provides: energy retention in high-speed maneuvers. One engineer attempts to explain this to a visiting naval officer using the captured Hellcat as a visual aid. The Americans have accepted a fundamental trade. They sacrifice sustained turn performance for everything else: speed, diving speed, acceleration, structural strength, pilot protection. In a turning fight, we maintain advantage. In every other engagement type, they dominate. The officer's response is telling. Then our pilots must force turning engagements. Sir, American pilots will not cooperate. They control engagement parameters because they control altitude and speed. This exchange, reported in multiple accounts from Yokosuka personnel, captures the strategic blindness that the captured Hellcat should have cured but couldn't. Japanese tactical doctrine had evolved around close-range dogfighting because Japanese fighters excelled at it. American tactical doctrine had evolved to avoid close-range dogfighting because American fighters didn't need it. The industrial philosophy that produced the Hellcat had also produced the tactics to exploit it. The armor plate examination reveals another dimension of American thinking: 212 pounds of steel protecting the pilot from multiple angles. The engineers test it: 7.7mm rounds fired from standard Japanese weapons. Complete penetration failure at combat ranges. 12.7mm rounds. Some penetration at close range, but most impacts are defeated or slowed sufficiently to prevent lethal injury. A Zero carries no armor. The philosophy was explicit: armor weight equals performance loss equals combat disadvantage. Better to avoid getting hit than to survive being hit. This made perfect sense when Japanese pilots had training advantages, when combat occurred at ranges where superior maneuverability mattered, when pilot quality was high enough that getting hit was relatively rare. By 1945, none of those conditions exist. Japanese replacement pilots with minimal training are being sent against American formations where every fighter carries armor and self-sealing tanks. The survival rates tell the story the engineers at Yokosuka already know. First mission fatality rates for Japanese pilots have become catastrophic. Most don't live long enough to gain combat experience. The ones who do survive describe the same scenario repeatedly: hitting an American fighter with what should be damaging fire, watching it continue to fight, eventually being forced to disengage because ammunition is exhausted and the target is still flying. Lieutenant Junior Grade Yoshio Fukui's report from his first encounter with Hellcats appears in the technical files. My aircraft took 17 hits in 3 seconds. Only by dropping into a spin did I escape. His Zero, examined after landing, shows 7.7mm holes throughout the fuselage. Had he been flying a Hellcat, most of those rounds would have been stopped by armor or absorbed by structural elements designed to take damage. The self-sealing fuel tanks represent another revelation. The engineers cut one open, examining the rubber composition and layered construction. When punctured, the material swells on contact with fuel, closing holes that would cause catastrophic leaks in Japanese tanks. It's elegant engineering applied to a problem Japanese designers had chosen to ignore because the weight penalty seemed too high. But there's a deeper insight here that the captured Hellcat makes unavoidable. The Americans didn't just add protective features, they redesigned the entire aircraft around those features. The armor isn't bolted on as an afterthought. It's integrated into the structure. The self-sealing tanks aren't modifications. They're part of the original design. The extra weight is distributed throughout the airframe in ways that maintain performance while adding survivability. This requires a level of design, integration that Japanese manufacturers, working under constant pressure to increase production and reduce weight, simply cannot match by 1945. The industrial base needed to support this philosophy. The precision machining, the quality control, the testing regimens has taken American industry years to develop. Japan doesn't have years. Japan has months before the strategic situation becomes completely untenable. The Pratt and Whitney engine receives the most intensive examination. Japanese engineers have experience with American radial engines through licensed production of earlier designs. Nakajima produced the Pratt and Whitney R-1340 Wasp under license in the 1930s, but the R-2800 represents a generational leap. The cylinder head design uses advanced metallurgy, valve springs that maintain tension through temperature extremes Japanese engines can't handle. Piston rings precision ground to tolerances that Japanese machine shops struggle to achieve consistently. The supercharger impeller is a single forging, balanced to specifications that require equipment Nakajima doesn't possess. One engineer writes in his analysis, "This engine is designed for mass production by semi-skilled workers. American philosophy assumes replacement rather than repair. Our philosophy requires repair because replacement parts are not available." The maintenance manual, translated with difficulty because technical English terminology doesn't always have Japanese equivalents, describes procedures that assume complete part interchangeability. A connecting rod fails? Replace it with a new one. No fitting required, no adjustment necessary. A cylinder develops cracks? Unbolt it, bolt on, a new cylinder. The manual lists replacement times in minutes, not hours. Japanese maintenance procedures, by contrast, assume parts must be fitted individually. A connecting rod replacement requires careful measurement, potential machining of mating surfaces, test fitting, adjustment. The same job that takes an American mechanic 20 minutes might require a Japanese mechanic 3 hours. Multiply this across an entire aircraft fleet, and the maintenance burden becomes crushing. The electrical system demonstrates American standardization philosophy at its most pragmatic. Color-coded wiring throughout. Standardized connectors that can't be connected incorrectly. Fuse boxes designed for rapid troubleshooting. Circuit diagrams printed on durable materials and mounted inside access panels. Every design decision prioritizes field serviceability by personnel who don't need to be electrical specialists. Japanese aircraft electrical systems, while functional, don't share this philosophy. Wiring diagrams exist but aren't mounted on the aircraft. Connectors vary by manufacturer and sometimes by production batch. Troubleshooting requires skilled electricians with specific training on each aircraft type. Again, this represents Japanese craftsmanship tradition meeting American industrial efficiency, and the comparison isn't favorable. The hydraulic system reveals similar thinking. Quick disconnect fittings that allow component replacement without draining the entire system. Filters designed for frequent changing. Reservoir caps that can be opened with one hand. Pressure gauges mounted for easy visibility. Everything designed around the assumption that maintenance will be required and should be as simple as possible. During one test flight, the Japanese pilot deliberately tests the Hellcat's structural limits. He performs a series of high-G maneuvers that would normally require post-flight inspection of a Zero's wing attachments. Pull 7 Gs, then 8, then 9. The wings flex, but don't fail. Control surfaces remain responsive. No creaking, no structural complaints. After landing, inspection reveals no damage. The pilot's report includes a critical observation. The Americans have designed their fighter to be flown by average pilots without catastrophic consequences. The Zero must be flown precisely within its envelope or structural failure occurs. This suggests American training philosophy differs fundamentally from ours. He's correct, though he doesn't fully understand why. American pilot training by 1944 emphasizes standardized procedures and systems management. Japanese training emphasizes individual skill development and aggressive tactics. American fighters are designed to be survivable when pilots make mistakes. Japanese fighters assume pilots won't make mistakes. The attrition rates prove which philosophy works better when pilot experience levels drop. The gun installation represents another example of systematic thinking. 6 Browning M2 50 caliber machine guns mounted in the wings. 2,400 rounds of ammunition. The guns are positioned to allow access for maintenance without removing the wing panels. Ammunition feeds are designed to prevent jamming. Spent casings are ejected in ways that won't damage the aircraft structure. Harmonization. The process of aligning the guns so their fire converges at a specific range uses standardized tools and procedures that any trained armorer can perform. Japanese fighters typically mount a mix of calibers, 7.7mm machine guns combined with 20mm cannons. The different ammunition types require different supply chains, different maintenance procedures, different harmonization techniques. American standardization on 50 caliber weapons simplifies everything from logistics to training to combat tactics. The structural examination produces perhaps the most significant findings. The Hellcat's airframe uses semi-monocoque construction, where the skin carries significant structural loads. This allows for damage tolerance that Japanese engineers find remarkable. Bullet holes in the skin don't necessarily compromise structural integrity because load-bearing members are redundant and internal. Engineers test this by deliberately damaging non-critical sections of the captured Hellcat structure, multiple bullet holes in the same fuselage bay. The structure remains sound. They compare this to a Zero's construction, where skin damage often means structural compromise, because the superduralumin alloy, while light and strong, becomes brittle when stressed and doesn't fail gracefully. The Americans have designed for battle damage. The Japanese have designed for performance. The captured Hellcat proves which philosophy keeps pilots alive. Production markings inside the airframe tell another story. Date stamps on major components show this aircraft was assembled in less than a month from parts manufactured at different facilities. The wings were built at one plant, the fuselage at another, the engine at a third. Everything came together at final assembly, with no hand-fitting required. The markings include inspector stamps, evidence of quality control processes that verify each component meets specifications before it goes to assembly. Japanese aircraft production, by comparison, often involves components being adjusted during assembly because they don't quite match. Inspectors exist, but they're checking for defects, not verifying that parts meet standardized specifications that ensure interchangeability. The difference seems subtle, but the implications for production rates are enormous. One engineer calculates the man-hours required to build a Zero versus the man-hours required to build a Hellcat. On the surface, the Zero should require less time, it's smaller, lighter, has fewer systems. But when he factors in the hand-fitting, the individual adjustments, the specialized craftsman labor, the numbers shift. A Hellcat, despite being larger and heavier, requires less skilled labor time because it's designed for assembly line production. This is when the true scale of American industrial capacity becomes undeniable. Grumman isn't building Hellcats the way Nakajima builds Zeros. Grumman is manufacturing Hellcats the way General Motors manufactures automobiles. The Bethpage, New York factory operates 24 hours a day, 7 days a week. At peak production, a new Hellcat rolls off the assembly line every 60 minutes. 60 minutes, the time it takes Japanese craftsmen to hand-fit a single Nakajima Sakaya engine's valve train. The comparison charts show 1944 Japanese fighter production, all types, 5,100 aircraft. 1944 American fighter production, 35,000 aircraft. Hellcat production alone, over 6,000 in a single year from a single factory. These aren't estimates. These are numbers confirmed through multiple intelligence sources, through captured documents, through simple observation of the number of American fighters appearing over Japanese-held territory. The mathematics are irrefutable. A senior officer reviewing the technical analysis asks the question everyone is thinking. Can we adapt these production methods? The answer comes from the engineering staff after careful consideration. Theoretically, yes. Given sufficient time to retool factories, train workers, establish quality control systems, develop supply chains for standardized parts, and create the institutional knowledge required to manufacture to these tolerances. Time required: 3 to 5 years. Resources required: industrial capacity Japan doesn't possess and cannot develop while under constant air attack. The practical answer is no, not by 1945. Not while American submarines are sinking the cargo ships that carry raw materials to Japanese factories. Not while B-29 raids are destroying manufacturing centers. Not while the best engineers are being diverted to desperate projects like kamikaze variants and last-ditch interceptors. The captured Hellcat becomes a monument to an uncomfortable truth. Japan entered the war with superior fighter pilots flying superior fighters. The A6M0 dominated Pacific skies for 18 months. But superiority based on pilot skill and aircraft performance has a fundamental weakness. Both deteriorate under attrition. Pilot skill requires time to develop. Aircraft performance requires resources to maintain. American superiority, built on industrial philosophy and systematic efficiency, doesn't deteriorate under attrition. It compounds. Every month, more Hellcats roll off assembly lines. Every month, more American pilots complete standardized training programs. Every month, the qualitative gap narrows while the quantitative gap widens. By January 1945, Japanese forces aren't fighting American fighters. They're fighting American industry. The final report on the captured F6F includes a section on lessons learned. The author, likely one of the senior engineers at Yokosuka, writes with unusual candor. The Hellcat represents a philosophical approach to warfare that Japan has not adopted and cannot now adopt. American aircraft are built to be produced rapidly, maintained easily, and flown by adequately trained pilots. Japanese aircraft are built to maximize performance for highly trained pilots. This was advantageous in 1941. It has become catastrophically disadvantageous by 1945. The industrial capacity that produces Hellcats has already won this war. We are examining the evidence of our defeat. The report is filed. Some officers read it. Most don't want to. The captured Hellcat sits at Yokosuka, occasionally examined by visiting pilots and engineers until American forces arrive in September. They find it damaged, cannibalized for parts, pushed into a dispersal area. An American GI poses next to it for a photograph, unaware that this particular aircraft taught Japanese engineers more about American industrial power than any intelligence report could have. Bureau number 71,441, one of 12,000. Built in less than a month, flown in combat for less than a month, captured and studied for months. And in that examination, Japanese engineers discovered what they'd been fighting all along. Not just better pilots or better tactics, but an entire civilization's approach to manufacturing warfare. The Hellcat's durability wasn't luck, it was design philosophy. The interchangeable parts weren't convenience, they were systematic efficiency. The armor and self-sealing tanks weren't luxuries, they were investments in pilot survival that paid dividends in sustained combat operations. Everything about the F6F represented choices that favored the long war over the short battle, industrial capacity over individual excellence, systematic advantage over momentary superiority. Japan had built the Zero to win battles. America had built the Hellcat to win the war. And by January 1945, the difference between those two philosophies had become impossible to ignore, even for engineers who desperately wanted to find a way forward that didn't end in surrender. The testimony comes from unexpected sources after the war ends, not from admirals or generals defending strategic decisions, but from the engineers and designers who spent their careers trying to match American production. Their words carry the weight of professional defeat, not military defeat, but the deeper recognition that their entire approach had been outmatched before the first shot was fired. Professor Jiro Horikoshi sits in the ruins of Mitsubishi's Nagoya plant in September 1945. The designer of the Zero, Japan's most iconic fighter, surveys the devastation. American B-29s have reduced Japan's premier aircraft manufacturing center to twisted metal and rubble. But the physical destruction isn't what haunts him. It's the realization that even if the factories had survived, even if the raw materials had been available, even if the workforce had remained intact, Japan still couldn't have won this industrial competition. In his post-war writings, Horikoshi describes examining a Hellcat at Yokosuka after the surrender. American occupation forces have collected captured Allied aircraft, and Japanese engineers are granted access as part of the technical exchange process. Horikoshi spends hours with the F6F, measuring, calculating, understanding. His conclusion, written in 1946, "We designed an aircraft for 1941, they designed an aircraft system for 1945. While we were perfecting the sword, they were building the industrial age." That phrase, aircraft system, captures what the captured Hellcat had revealed. The Americans hadn't just built a better fighter, They'd built an entire ecosystem around fighter production. The standardized parts, the interchangeable components, the simplified maintenance, the pilot protection, the production capacity. These weren't separate features. They were integrated elements of a systematic approach to air warfare that Japan never developed because Japan never needed to develop it. Until it did, and by then it was too late. The numbers tell the story in stark mathematical clarity. Total F6F Hellcat production from 1942 through 1945, 12,275 aircraft. Total Mitsubishi, a 6M0, production from 1940 through 1945, 10,449 aircraft across 5 years from 2 major manufacturers. The Americans produced more of a single fighter type in 3 years than Japan produced of its primary fighter across the entire war. But production numbers only tell part of the story. Survival rates tell the rest. By late 1944, the average American carrier fighter pilot survives 14.2 combat engagements. The average Japanese fighter pilot survives 2.3. American pilots are surviving longer, gaining experience, becoming more dangerous. Japanese pilots are dying before they complete their 3rd mission, taking their limited training with them, forcing Japan to send even less prepared replacements into combat against increasingly experienced American opponents. The death spiral becomes unstoppable. Lieutenant Commander Saburo Sakai, Japan's leading surviving ace, describes the situation in his post-war memoirs with brutal honesty. By 1945, most of our fighter pilots were boys with 40 hours of training. They couldn't dogfight, couldn't navigate properly, couldn't land on carriers consistently. The Americans shot them down like clay pigeons. Not because American pilots were necessarily more skilled, but because American aircraft kept their pilots alive long enough to become skilled. The Hellcats' armor plate and self-sealing tanks, which seemed like expensive luxuries to Japanese engineers designing for maximum performance, turned out to be strategic investments that paid exponential returns. An American pilot hit by gunfire had a reasonable chance of returning to his carrier, getting his aircraft repaired or replaced, and flying again the next day. A Japanese pilot hit by gunfire usually died because his unarmored cockpit offered no protection, and his non-self-sealing tanks turned bullet strikes into fireballs. The training difference compounds the hardware difference. By 1944, American pilots entering combat have 250 hours of flight time, including extensive gunnery practice, navigation training, and tactical instruction. They've flown multiple aircraft types, understand their aircraft systems thoroughly, and have been taught both offensive and defensive tactics. Japanese replacement pilots in the same period have 40 to 60 hours of flight time, minimal gunnery practice, and basic flight skills that often don't include night operations or bad weather flying. But even if Japan had possessed the fuel to extend training, even if the instructors had been available, even if the aircraft could be spared from frontline service, the fundamental problem remained. Japanese fighters weren't designed to keep novice pilots alive long enough to gain experience. American fighters were. The Hellcat's forgiving flight characteristics, its wide landing gear stance that reduced carrier accidents, its visibility from the cockpit, its backup systems, all of these features worked together to prevent training accidents and combat losses among inexperienced pilots. The Yokosuka engineers who examined the captured Hellcat understood this. Their reports, declassified decades after the war, show they grasped the implications. One analysis from March 1945 states, American fighter design philosophy assumes average pilotability and builds aircraft systems to compensate. Japanese design philosophy assumes exceptional pilotability and builds aircraft to maximize performance for such pilots. The American approach is sustainable, ours is not. But understanding a problem and solving it are different challenges. By March 1945, Japan doesn't have the industrial capacity to implement American-style production even if the political will existed. The submarine blockade has reduced raw material imports to a trickle. The strategic bombing campaign is destroying what manufacturing capacity remains. The workforce is depleted by military conscription and malnutrition. The infrastructure for precision manufacturing, the machine tools, the quality control equipment, the testing facilities has been degraded beyond rapid recovery. Japan's aircraft production numbers for 1945 tell the story of industrial collapse. January, 420 fighters produced. February, 370. March, 340. By August, production has virtually ceased, not because factories have stopped trying, but because the raw materials aren't available, the electrical power is unreliable, the transportation networks have been destroyed, and the workers are spending more time in shelters than on assembly lines. Meanwhile, American production continues to accelerate. April 1945, 560 Hellcats manufactured. May, 600. The gap isn't closing, it's widening. Every month, the Americans add more combat-capable fighters to their inventory than Japan produces of all aircraft types combined. The kamikaze program, implemented in October 1944, represents the ultimate admission of conventional combat failure. Vice Admiral Takejiro Onishi, organizing the first kamikaze units, justifies the program with brutal mathematics. If a Zero attacks conventionally, probability of success approaches zero. The Hellcats will destroy it. If the Zero becomes a guided bomb, probability of hitting the target increases to 30%. The pilot dies either way. At least as a kamikaze, his death has meaning. This calculus would have been unthinkable in 1942 when Japanese fighters dominated Pacific skies. But by late 1944, Japanese fighter pilots can no longer compete with American fighters in conventional combat. The hardware gap, the training gap, the experience gap, the industrial support gap, all have become insurmountable. Suicide attacks aren't a tactical choice. They're the last option when all conventional options have failed. The captured Hellcat at Yokosuka witnesses some of this transformation. Before it's permanently grounded by mechanical problems, Japanese pilots practice against it in mock combat. They learn, as American pilots learned in 1943, that you don't dogfight with the aircraft's strengths, you exploit its weaknesses. For the Hellcat, that means turning combat at low speed. But the mock combat exercises prove what real combat has already demonstrated. American pilots won't cooperate. They dictate engagement parameters through superior altitude and speed control. They attack when they have advantage and disengage when they don't. And Japanese fighters, lacking the performance to force engagement on their terms, can't stop them. One Japanese pilot, flying an A6M50 against the captured Hellcat in a training exercise, reports, "The American fighter's weight should be a disadvantage in maneuvering combat. But if the American pilot refuses to maneuver, if he uses only speed and altitude, his weight becomes an advantage because it provides energy in high-speed flight. We have designed our fighters for combat scenarios our enemy will not accept." This insight, replicated across hundreds of combat encounters, explains the 19-to-1 kill ratio the Hellcat eventually achieves. It's not that American pilots are 19 times more skilled. It's that American tactical doctrine, supported by American aircraft capabilities, creates engagement conditions where American advantages compound while Japanese advantages become irrelevant. The occupation period brings the final revelations. When American engineers tour Japanese aircraft factories in September and October 1945, they document production methods with professional curiosity. The reports describe skilled craftsmen hand-fitting components, improvising solutions to parts shortages, maintaining production against overwhelming odds. There's respect in these accounts for Japanese ingenuity and dedication. But there's also recognition that Japanese manufacturing philosophy, however skilled, couldn't compete with American industrial systems. One American engineer, examining a partially completed Zero at a Nakajima plant, writes, "This aircraft represents thousands of hours of skilled labor. The craftsmanship is excellent, but the production rate is too slow, the parts aren't interchangeable, and field maintenance requires specialized expertise. They've built a sports car when the war required trucks." The metaphor is apt. The Zero was a masterpiece of lightweight engineering, a triumph of making the absolute most from limited resources. But it was optimized for a short war where initial superiority could be converted into decisive victory. The Hellcat was engineered for a long war where sustained production, pilot survivability, and logistics support mattered more than peak performance. Professor Horikoshi, in his most candid post-war assessment, acknowledges this. The Zero was the best fighter we could build with the resources and philosophy we possessed in 1937, but we should have recognized by 1942 that the war's outcome would be determined by industrial capacity, not aircraft performance. We couldn't recognize this because our entire military tradition emphasized quality over quantity, individual excellence over systematic advantage. The Americans understood that modern warfare is fundamentally industrial. We didn't, and we paid for that failure with hundreds of thousands of lives. The institutional learning process proves painful. Japanese engineers and designers, many of whom will go on to rebuild Japan's post-war aviation industry, internalize lessons from the captured Hellcat and other American aircraft. When Japan begins manufacturing aircraft again in the 1950s, the influence is obvious. Standardized parts, simplified maintenance, quality control systems, production methods borrowed directly from American practices. The craftsmanship tradition remains, but it's integrated into systematic manufacturing rather than replacing it. The irony doesn't escape the engineers who examined the captured Hellcat in 1945. They spent months studying American industrial methods, understanding the philosophy, recognizing the implications. And they couldn't implement any of it because the war was already lost and the industrial capacity to make changes no longer existed. Knowledge without the ability to act on it, understanding without the resources to adapt. The captured Hellcat taught them how they could have built better fighters, but only after it was too late to matter. Commander Charles August, whose forced landing on Taiwan provided Japan with that educational opportunity, survives his captivity. The Omori POW camp near Tokyo, where he's held, subjects prisoners to regular beatings and starvation rations. August endures until liberation in August 1945. He'll eventually retire from the Navy as a commander in 1962, having served in Korea and NATO assignments. He dies in 1985, probably never knowing that his aircraft became one of the most thoroughly examined F6Fs in Japanese hands. Bureau number 71441 ends its service in a dispersal area at Yokosuka, cannibalized for parts, damaged beyond economical repair. When American forces discover it in September 1945, they document it with photographs and disposition reports. The aircraft isn't preserved. It's likely scrapped, along with thousands of other Japanese aircraft in the post-war cleanup. One airframe among millions, unremarkable except for the education it provided to engineers who finally understood what they'd been fighting. The preserved reports from that examination, residing in Japanese and American archives, tell a story that transcends individual aircraft specifications. They document the moment when Japanese engineers confronted the full scope of American industrial philosophy and recognized that Japan had brought craftsmanship to a manufacturing competition. Superior skill versus superior systems. Individual excellence versus institutional capability. The sword versus the assembly line. In 1962, the United States Navy holds a symposium on Pacific War aviation. American and Japanese veterans gather to discuss the conflict with 2 decades of perspective. Captain David McCampbell, the Navy's ace of aces with 34 victories, states simply, "The Hellcat won the Pacific Air War, period. It destroyed Japanese aviation and made our victory inevitable." Commander Saburo Sakai, invited to provide the Japanese perspective, responds with characteristic bluntness. The Zero was a superior fighter. The Hellcat was a superior weapon system. We never understood the difference until too late. We brought swords to a gunfight and wondered why we lost. The audience, composed of engineers and pilots who lived through the war, understands exactly what Sakai means. A superior fighter is an aircraft with better performance specifications. A superior weapon system is an integrated approach to design, production, logistics, training, and tactics that multiplies individual capability through systematic advantage. Japan perfected the former, America perfected the latter. And the war proved which approach matters more when conflicts extend beyond initial clashes into sustained industrial struggles. The final statistics confirm what the captured Hellcat revealed to Japanese engineers in January 1945. F6F Hellcat total aerial victories: 5,223 enemy aircraft destroyed. Hellcats lost to enemy action in the air: 270. Kill ratio: 19.3 to 1. No other fighter in history has achieved such dominance over such a sustained period against such a determined enemy. But that 19 to 1 ratio isn't just about individual pilot skill or aircraft performance. It's about American pilots flying aircraft designed to keep them alive long enough to gain experience, maintained by systems that kept those aircraft combat-ready, supported by industrial capacity that replaced losses faster than combat could inflict them, and employed in tactics that exploited systematic advantages rather than relying on individual brilliance. The Japanese engineers at Yokosuka understood this. By the time they finished examining the captured Hellcat, every bolt they removed, every system they tested, every specification they measured, taught them the same lesson. They weren't fighting American fighters. They were fighting American industry, American logistics, American training systems, American production philosophy, American institutional capability. The Hellcat was simply the most visible manifestation of that systematic approach. One engineer, in the closing section of the technical analysis report, writes what might be the most honest assessment produced by any Japanese military institution during the war. "We have examined this aircraft thoroughly. We understand its capabilities, its design philosophy, its production methods. We recognize that we cannot replicate these methods with available resources. More significantly, we recognize that even if we could replicate these methods, we lack the industrial base, the resource access, the time, and the institutional knowledge to implement them at scale. The Americans have not built a better fighter. They have built a better system for producing, maintaining, and employing fighters. That system has already won this war. We are simply waiting for the mathematics to resolve into surrender." The report is dated March 19, 1945, 4 months and 26 days before Japan's surrender. The engineers at Yokosuka knew the outcome before the atomic bombs, before the Soviet declaration of war, before the final collapse. They knew because they'd examined the evidence, they'd measured the tolerances, documented the systems, calculated the production rates, understood the philosophy. The captured Hellcat taught them everything they needed to know about why Japan was losing and why that loss was inevitable. The morning Lieutenant Charles August force-landed his Hellcat on Taiwan. He couldn't have imagined his aircraft would become a monument to industrial philosophy. But Bureau number 71441 served Japan better as an educational tool than it had served America as a fighting machine. It taught Japanese engineers the truth about modern warfare, that durability beats performance, that systematic production beats craftsmanship, that protecting pilots beats maximizing aircraft capabilities, and that industrial capacity determines outcomes more decisively than individual excellence. Those lessons would eventually help rebuild Japan into an industrial powerhouse, but in January 1945, they simply confirmed what careful observers already suspected. The war was over. It had been over since America's industrial base fully mobilized, since Ford and General Motors started building fighters on assembly lines designed for automobiles, since Pratt and Whitney began producing engines with interchangeable parts that could be maintained by mechanics instead of craftsmen, since Grumman designed a fighter that prioritized pilot survival over peak performance. The Hellcat didn't just sweep Japanese aircraft from Pacific skies. It demonstrated that modern war belongs to nations that can industrialize violence, that can produce capability faster than combat can degrade it, that can protect their trained personnel long enough for that training to compound into experience. Japan's engineers learned that lesson by examining Bureau number 71441. They learned it thoroughly, professionally, and far too late to matter. The captured Hellcat at Yokosuka taught them they'd never built durability like it. But more than that, it taught them they'd never built a system like the one that produced it. And that difference between building aircraft and building systems for producing aircraft explained everything about why the rising sun was setting over the Pacific in January 1945. Thank you for watching. For more detailed historical breakdowns, check out the other videos on the Dexpert Every Pose in your screen now, and don't forget to subscribe.